part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to continue the discussion of hollow conducting waveguides. Last time around, we spent a great deal of time delving through looking at how the longitudinal and transverse components were related to each other. So remember, a waveguide is oriented such that it lies along the z-axis. And the z-axis is longitudinal in this case, and the x and y components are transverse. And we'll assume that our waveguide is of dimension A in the x direction and dimension B in the y direction. We were interested in the propagation of harmonic oscillations. So we assume that the wave propagates in the z direction, and each, or I should say both, electric and magnetic fields have a factor of e to the ikz minus omega t in common, and these are complex amplitudes, are not constant in this case, in fact, depend on the transverse components x and y. And notice I've written tildes or drawn tildes over the vectors, and the reason for that is because we are working in complex notation. Remember, ever since we started talking about electromagnetic waves, it's just a lot more convenient to use complex notation and work with exponentials rather than using trigonometric functions. So we were interested, or we're still interested, in solving the wave equation. And both the electric and magnetic fields are solutions of the wave equation. And since we're working with a rectangular system, we're going to break this down into Cartesian components. So this is partial derivative, second partial derivative with respect to x, plus second partial derivative with respect to y, plus second partial derivative with respect to z, minus 1 over c squared, partial derivative with, or second partial derivative with respect to time. I'm going to go ahead and write this as I have up here. This is the complex amplitude, and this is e to the I kz minus omega t, and not down here, this is e to the I kz minus omega t. Okay, so I can't get too far yet with the partial derivatives with respect to the transverse components. The partial derivative with respect to z, the amplitudes out front don't depend on z, so I'm just taking the partial derivative twice with respect to z of this. So this gives me an ik times an ik, which is equal to minus k squared. If I take the second partial derivative with respect to time, that's going to give me minus omega squared. I might as well replace these two terms by minus k squared and plus omega squared over c squared. And now I can just drop out the exponentials. And our complex amplitudes are solutions of this equation. I introduced one other term that I didn't get around to hashing out last time around. Anyway, this is the cutoff wave number. And that's equal to omega squared over c squared minus k squared. I'm going to flip it around. I'll write this as k squared is equal to omega squared over c squared minus kc squared. And this is called a dispersion relation. spent a lot of time writing out the longitudinal component, or I should say the transverse components, in terms of longitudinal components, and the reason I gave for that is that it facilitates the solution of this equation, of this differential equation. Because then I can just solve for the longitudinal component and then work out everything else from that one, solving that one problem. We also talked about transverse electromagnetic, transverse electric, and transverse magnetic. I showed last time around that transverse electromagnetic waves do not exist. Don't propagate inside of hollow conductors. They certainly exist in if the waves are propagating in infinite space. I mean, when we first talking about plane waves, I've mentioned, well, your wave vector is pointing one way, your electric field is perpendicular to the wave vector, and then your magnetic field is perpendicular to both the wave vector and the electric field. But these don't exist for hollow conductors. They do exist for coaxial conductors, but we're not going to get into that in this class. However, transverse electric and transverse magnetic waves do exist. I'm going to investigate just transverse electric waves. That's typically the case in most textbooks. The authors will go over transverse electric and then they'll give the students transverse magnetic. I will give you the general solution, or I guess not quite to the end, but just part of the solution of transverse magnetic. And once you see how to work through transverse electric, you can follow basically the same kind of procedure for the transverse magnetic. Now remember, the boundary conditions are different, so I will certainly make a note of that when I get to that point. But anyway, we're looking at transverse electric, so that means that the Z component of the electric field is 0. Okay? Now, we are working in terms of the amplitudes. We already know what the dependence on Z is. And we're using complex notation to facilitate the analysis. So that longitudinal component is 0. However, longitudinal component of the magnetic field is most certainly not 0. So this is what I'm going to solve for first. Haven't done one of these problems in quite some time, but if you think back to electrostatics, we solved problems of this kind using boundary value, separation of variables. Okay? When I say problems of this kind, it's not quite the same thing, but it's close. And by using separation of variables, we're assuming that our magnetic field can be written as a function, or the product of a function of x only and a function of y only. Now notice I am going to retain the tilde over b. I'm not going to leave it on the x and y just because the notation is getting a little bit awkward at this stage of the game. But when I plug this into my differential equation, what I'll wind up with is 1 over the function x, second derivative of the function x with respect to the variable x. And notice we're no longer talking about partial derivatives. A second term gives me 1 over y second derivative of the function y with respect to the variable y plus kc squared, and all that has to be equal to 0. Well, the only way this equation is going to hold for arbitrary x and y is that this is a constant and this is a constant. And it's convenient to choose this first term equal to some constant minus kx squared, and the second term is equal to minus ky squared. So when I solve this problem and this problem, I'll solve a differential equation of the form second derivative of the function x with respect to x plus kx squared function x is equal to 0. Second term gives me second derivative of the function y with respect to y plus ky squared times the function y is equal to 0. So right away, what are the solutions to these? Well, cosine and sine. So therefore, x is equal to some constant c1 cosine x, x plus c2 sine x, x, and function y is equal to c3 cosine case of y, y plus c4 sine case of y, y. I can't go any further until I impose the boundary conditions. Well, boundary conditions for this case are that the tangential component of the electric field is 0 on the surfaces, and the normal component of the magnetic field is 0 on the surfaces. However, we derived another form of the boundary conditions, which is most convenient for this the way the differential equation is written and what we're solving for. So that the z component of the magnetic field with, or I should say the partial derivative of the z component of the magnetic field with respect to the normal is equal to 0 on the surfaces. So again, we are looking at the amplitudes here, and again, we're treating this as a complex number. And remember, we've left off the complex notation over here. Basically, it would just be the c's that were complex, and the reason I'm doing it is because I don't know, the notation's starting to look a little bit awkward at this stage, so I'm just going to leave it off. Just bear in mind it's possible that the coefficients might be complex. Okay, so our boundary conditions, let's take the x direction. So we take the normal to the left-hand side, or partial derivative with respect to the normal, so that would be partial derivative with respect to x. We're going to evaluate at x equals 0, but it also must hold at x equals a as well. When I take the derivative with respect to x of this function, this first one here will give me a sine times c1 minus kx, and if that's automatically equal to 0 at x equals 0. Now, the second term, however, when I take the derivative, I'm going to have some coefficients, constants out front, basically times cosine kx x. Well, kx will be cosine of 0, which is 1. So the only way that second term is going to vanish at x equals 0 is if we just take c2 equals 0. Now, to satisfy the second condition, that the partial derivative with respect to the normal must vanish at x equals a, well, that's minus kx c1 times sine kx and a. Kx times a is equal to 0. The only way this is going to hold is if kx is equal to n pi over a. I'll do the same thing for the y components, y direction as well. Again, when we take the derivative with respect to y, this first term will automatically be 0 at y equals 0. When I take the derivative of the second term, however, that is the only way that term is going to vanish is if I set c4 equals 0. And likewise, the only way that'll hold is if this argument is some integer value times pi. So Therefore, ky must be equal to n pi over b, and again, m and n are integers. And the solution, therefore, is going to be equal to assume constant times cosine of n pi x over a times cosine n pi y over b. And that's the solution of the differential equation. Again, I'm going to leave the tilde over top to take possible account that B naught might be complex. I'm going to have to erase most of this, so let me just leave this up here for a minute. So I've just written the cutoff wave number, and we figured out that kx had to be equal to n pi over a, ky had to be n pi over b, and so therefore kc squared is equal to the sum of the squares of those two. And we transferred the expression for the longitudinal component of the magnetic field over here, and now that I've figured that out, I can calculate the transverse components of both the electric and magnetic fields, knowing what the longitudinal component of the magnetic field is. Anyway, we derived these expressions, or relations I should say, in the previous lecture, and I'll read them off. This is the x component of the electric field is equal to I omega over kc squared, partial derivative of the longitudinal component of the magnetic field with respect to y. The y component of the electric field is equal to minus I omega over kc squared, and that's times the partial derivative of the longitudinal component of the magnetic field with respect to x. Now, B naught x, the x component of the magnetic field, is equal to ik over kc squared, partial derivative of the magnetic field, longitudinal component of the magnetic field with respect to x, and B naught y is equal to ik over kc squared, partial derivative of the longitudinal component of the magnetic field with respect to y. If you haven't watched that video and you don't know where these expressions came from, I urge you to go back and take a look at that before we continue. But in any case, I've got these written in terms of the amplitudes, which of course are not constant. They do depend on x and y. But I'm interested in the full solution, so let me just take these knots off here. And by the way, this exponential actually is e to the I kz minus omega t. I'm just running out of room here, and I actually do need to leave this up on the board for what I'm going to cover next. So let me just write it out like this. Second term Okay, so those are your complete solutions, but of course, at the end of the day, we do want to take the real part of this because this is still in complex notation. But anyway, let me just maybe not read off everything in excruciating detail, but both of the electric fields have a factor of I omega over kc squared out front. EY also has an additional minus sign. Here we have the complex constant amplitude V naught, and each of these terms has that factor. This top term we have, because we're taking the derivative, has a factor of minus n pi over b. This is minus n pi over a, minus n pi over a, and minus n pi over b. So we have, this is the x, cosine of the x, or function of x rather than function of y. So this is cosine, sine, sine, cosine, sine, cosine, cosine, sine, and then times the exponential. So let me just leave that up there for a minute so you can copy it down and take everything in. So as I mentioned, I do want to take the real part of it, but before I do that, I want to flesh out a little better what I mean by the term cutoff wavelength, or cutoff frequency, I should say. Okay. Well, cutoff frequency, we'll write that as omega mn. Subscripts, of course, pertain to the m and the n up there, and this is equal to c, the speed of light, times k mn. And I'm going to put a little subscript c there, and that is equal to c times pi times the square root of m over a squared plus n over b squared. Okay? Now, remember our dispersion relation. That was equal to k squared is equal to omega squared over c squared minus kc squared. Remember, we came up with this because we wrote out, actually used kc basically as a separation constant when you're analyzing the wave equation. And once we solved for the longitudinal component of the magnetic field, figured out that kc has to have this form. So that's where that comes from. Can you see what happens here? Omega represents the driving frequency. And let me go ahead and replace this kc squared by omega mn squared over c squared. The driving frequency, omega, has to be larger than the cutoff frequency, otherwise the waves won't propagate. You see right here, if omega happens to be less than omega mn, then k is going to be imaginary, and you don't have a propagating wave. In other words, the wave isn't going to travel down the waveguide carrying energy with it. Essentially, the wave is going to be evanescent. Okay? Well, let's take a look at what these meant by the mode. These are transverse electric waves that we're dealing with. So the mode is indicated by the subscripts m and n. Now the dominant mode is TE10. So in other words, m is equal to 1, n is equal to 0. So how do I know it's the dominant mode? Well, by convention, we assume that the first index corresponds to the larger dimension. So notice I've drawn this rectangular waveguide here. noise. In commercial waveguides, the dimension A is roughly twice as large as dimension B. It's not exactly 2. And the reason why that choice is made is because that maximizes the single mode bandwidth. So what do I mean by that? Well, let's take a look at our dominant mode more closely. So omega 1, 0 in this case is equal to C pi over A. And I have been calling this frequency, it really is angular frequency, but a lot of people are a little sloppy with the terminology. I suppose it's no excuse, but anyway. The frequency, of course, is just the angular frequency divided by 2 pi. And that's equal to C over 2A for the dominant mode. And furthermore, the wavelength is equal to 2A. So if A is the larger dimension of these two sides, then that means that the frequencies corresponding to, say, the 0-1 mode are going to be larger. Okay? So in this case, the angular frequency, cutoff frequency is going to be C pi over B. Actual cutoff frequency is C over 2B, and the cutoff wavelength is going to be 2B. Let's put in some numbers here. Let's suppose that our waveguide is 2 centimeters wide, and I don't need to grab a calculator. We'll just assume B is equal to 1 centimeter. So it won't be precisely twice as large, but that's what I'm assuming for the sake of this example. Okay, so if we look at what the frequency is, the cutoff frequency in this case, well, C represents the speed of light, so that's 3 times 10 to the 8th meters per second. And therefore, cutoff frequency for the dominant mode is going to be 0.75 times 10 to the 10 hertz. The cutoff frequency for the 0-1 mode is going to be twice that, 1.5 times 10 to the 10 hertz. What I mean by single mode bandwidth is the range of frequencies for which only one mode propagates. You see, if I had the driving frequency anywhere between 0.75 and 1.5 times 10 to the hertz, the only mode that's going to propagate there is going to be the TE10 mode. Any higher modes, well, are too high and the wave will not propagate, it'll be evanescent. Okay? And in fact, for these particular numbers that I've chosen, mu20 will also be equal to 1.5 times 10 to the 10 hertz. And it's usually the case that you want to have just one mode propagate, or I should say for many applications, because if you have additional modes propagating, that coupling can occur. And that complicates things, and as far as a lot of engineers are concerned, this is not a good thing. So if you just want to have one mode propagate, well, then you choose with this dimension, these dimensions of the waveguide, you choose a frequency, driving frequency that was somewhere between these two quantities, okay? So cutoff frequency, that means the minimum frequency of the wave that can propagate. So any driving frequency has to be larger than this value. Okay? Just leave that up there just for a minute. And since we are talking about the dominant mode, I want to look at the components of the electric and magnetic field or the dominant mode. case, for the dominant mode, m is equal to 1, n is equal to 0. Plug n equals 0 here, and I see E of x is 0. And also, b sub y is 0. E sub y, however, is equal to I omega over kc squared, the amplitude b naught, complex amplitude, times pi over a sine pi x over a, and e to the I kz minus omega t. So I'll write out the exponentials here. Okay, and b sub x is also going to be non-vanishing. And let me go ahead and write out the full longitudinal component of the magnetic field. Okay. Unfortunately, I'll have to leave this up over here and let me erase the left-hand side. Or I should say, unfortunately, I have to erase the left-hand side. I'll leave that up over there. Okay, so notice I've expressed this in some complex amplitude B naught. Sometimes it might be more convenient if I express these amplitudes in terms, instead of B naught, in terms of E naught. So let's say that B naught is equal to I. B naught times I omega over kc squared pi over A. But we know that kc is equal to pi over A squared, so this becomes B naught I omega A over pi. Okay? And I'll make these substitutions in the rest of the expressions. Now I'm expressing the transverse components of the electric and magnetic fields in terms of the peak electric field. we'll do as well is use the Euler relation to replace the exponential by cosine and sine. So this becomes cosine kz minus omega t plus I sine kz minus omega t. And as I said, we want to take the real part, so E sub y is equal to E naught sine pi x over a times cosine kz minus omega t. Bx is equal to minus k over omega E naught sine pi x over a cosine kz minus omega t, and then last but not least, bz is equal to pi E naught over omega a cosine pi x over a sine kz minus omega t. So those are the fields for the dominant mode, okay? And also expressed in terms of peak amplitude E naught, which is a real quantity. Now I didn't really have to do this per se. The only effect of including, making this amplitude B naught complex is it basically will change around this cosine. This would be a sine, sine, and cosine. So it's just basically, it's just BZ is out of phase from these other two components. Okay. Okay, so I'm going to have to erase this on the left-hand side of the board because next I'm going to calculate the power that's transported down the waveguide. And to start out, we need to figure out what is the time average pointing vector. And if you recall from an earlier lecture, that's equal to 1 over 2 mu times the real part of the cross product of the electric field and the complex conjugate of the magnetic field. So we've got a few components here. This is 1 over 2 mu naught. Again, real part. So if I look at the cross product of the electric field and the x component of the complex conjugate of the magnetic field, what you'll see is these two guys together here, that's actually going to be a real number. So I'll get to that in a minute. However, if you look at the cross product, if you look at the y component of the electric field and the cross product of that with the complex conjugate of the z component of the magnetic field, you notice you're going to have an extra factor of I there. So that product is going to be pure imaginary. You know, when you take the complex conjugate here, these exponentials for the magnetic field are going to become e to the minus I kz minus omega t. So when you take the product of this and this or this and this, the exponentials are just going to cancel each other out. Therefore, you're just going to have one term surviving. This is 1 over 2 mu naught. Real part And this is y cross x, which gives us a minus z caret. And we'll have iy, or I omega, over kc squared, b naught, pi over a, sine pi x over a, e to the I, kz minus omega t. And now for the x component, take the complex conjugate of that, minus I is actually just going to become I. Kc squared. The complex conjugate of the amplitude being out there. And you see from this here, this is going to be a real number. And if you went through and wrote everything out for the y cross z term, that's going to be pure imaginary. So take the real part of something that's pure imaginary. Of course, that contributes nothing here. This is 1 over 2 mu naught in the z direction. I've got essentially minus I times I. That's just going to be equal to 1. And I have k omega times kc, or rather I should say kc to the fourth, and I've got pi over a times pi over a, and then when I take the product of the complex conjugate of b naught with itself, that just gives me b naught squared, that's just a real number. And the two signs give me sine squared pi x over a, and this e to the I kz minus omega t cancels out with e to the minus I kz minus omega t. And again, the second term, y cross z term, is going to be imaginary, so when I take the real part of that, of course, that just drops out. Okay, so that is the time average pointing vector. Let me erase this. Because after all, it is the power that we want to calculate. I'm going to integrate this pointing vector over the cross-sectional area of the waveguide. And the normal to this cross-sectional area will, of course, be in the z direction. Got 1 over 2 mu naught. And we'll have a factor of k omega in the numerator. In the denominator, we've got kc to the fourth. Now remember, we are looking specifically at the dominant mode, so therefore kc to the fourth is equal to pi over a to the fourth. So that's going to cancel out with, partially be canceled by this pi over a squared term. When you integrate in the y direction, there is no dependence in this expression on y, so that's just going to be a factor of b. And it's a little scrunched up at the end here. I also integrate from 0 to a, and this time I'm integrating the function sine squared pi x over a. When I do that, that's going to be a over 2. And again, the integration in y direction just gives me a factor of b. And there's your answer. Amount of power transported down waveguide by the dominant mode is equal to k omega over 4 mu naught, a over pi, quantity squared, ab, b naught squared. Now, again, it's oftentimes more useful to express this power in terms of the peak electric field rather than in terms of the peak magnetic field, or rather I should say the magnetic field. So anyway, when we square b naught squared, from over here, it's just equal to e naught squared pi squared over omega squared a squared. KAB over 4 mu naught omega E naught squared. So that's in terms of the peak electric field that exists inside of the waveguide. And there's another useful way of expressing this as well. So I'm going to rewrite this as K squared is equal to K naught squared minus KC squared. So I haven't used the term K naught yet, but basically this is the free space wave number. And this is a cutoff wave number. Okay. So we write this as replace K by the free space wave number and the cutoff wave number. And remember, your wavelength is related to the wave number by K is equal to 2 pi over lambda. K naught is equal to 2 pi over lambda naught. And Kc is equal to 2 pi over lambda c. So again, the knots refer to the free space, the c's refer to the cutoff, and if we don't have any subscripts at all, that actually is the effective wavelength for the waveguide. This is the effective wave numbers. Okay? So in this case, we have I'm going from this step to this step. I've just got the AB E naught squared over 4 mu naught omega times 2 pi over lambda naught. Remember, that's how the wave number and the wavelength are related to each other. Square root of 1 minus Kc squared. We're dealing with the dominant mode, so the Kc in this case is just equal to pi over A. So we're squaring that, that's pi over A squared. And I'm replacing K naught by writing that rather in terms of the free space wavelength. So that's just lambda naught over 2 pi quantity squared. And this is equal to K naught. And what's K naught over omega equal to? It's equal to 1 over C. And that's how K naught and omega are equal to each other. And that is the power that's transmitted, expressed in terms of the peak amplitude, and also expressed in terms of the free space wavelengths. You see, once you know what the frequency, the driving frequency is, you can just figure out what lambda is, because C is just equal to lambda times frequency. And what's E naught equal to? Well, this presents an interesting point here, because even though we've derived these expressions assuming basically that we've got a vacuum on the inside, it's without too much error. You can say, well, maybe there's error inside. Okay, refractive index of error obviously is just a little bit above 1. So without too much error, we can make an estimate here. The peak electric field before you have electric breakdown is 3 times 10 to the 6 volts per meter. So in that case, you can figure out what's the peak power that can be transported down this waveguide in any kind of real circumstances. So I like this problem because, you know, we started out with, we were doing electrostatics with very abstract problems. We were talking about spheres, infinite cylinders, infinite planes, and the goal there was to teach you to understand the behavior of these simpler systems. But now we're getting to the case where we're actually doing a problem that has real application. Granted, any engineer, of course, is going to say, well, that's not a perfect conductor, we need to take account of that, and that's true. But without too much error, we can estimate how much power can be transported down the waveguide, okay? And max power transported based on what's the electrical breakdown of error, okay? And since we're talking about energy being transported, it might be interesting to answer the question, with what speed is the energy transported? So let me erase this. It turns out there are several velocities. There's the phase velocity, and then there's the group velocity. Phase velocity is just equal to omega over k. So using my dispersion relation, omega over k. And C flips up into the numerator. If I divide every term through by a factor of omega, we'll get rid of the 1 in the numerator. This becomes 1, and this is 1 minus omega mn over omega squared. Now, because this quantity in the denominator is definitely going to be less than 1, what does that mean? Well, what that means is is that your phase velocity is actually going to be greater than the speed of light. You think to yourself, oh my gosh, we must have made some horrendously bad mistake. Well, not quite, because it turns out the energy is transported at the group velocity, not at the phase velocity. And group velocity is the derivative, or 1 over the derivative of the wave number with respect to omega. And that is definitely less than the speed of light. You can actually show that explicitly for this problem, and not just for the dominant mode, but for arbitrary modes by calculating the power, as we did, and then also calculating the energy density and integrating over the cross-sectional area, taking the ratio of those two. You'll see that the group velocity, or rather the energy, is transported at the group velocity. Okay?